Let's understand what is escape velocity. Let this be Earth. We can take any planet. Its mass is m. Because of this mass, it's a big mass, you'll have a potential at gravitational potential at the surface. So you'll have gravitational field around it. You'll require to have a kinetic energy to overcome this gravitational potential. Potential energy will be equal to kinetic energy. Only then this will be able to escape this. You have a potential that is holding it to this. So you need energy to get out of it. What will be that energy? If you are given certain velocity, because of which your energy equals to this gravitational potential, then you'll be able to escape this gravitational field of this particular planet. That is called escape velocity. So let's take the example of Earth. We know that the potential on let's start from this point. Let's say we are talking at a distance x, not like this. Let this be x. So what is the potential at this point? Or we can start from scratch. What is the force experienced by a body of mass m at this point? It will be gmm by x square. So this is the force experienced by a body of mass m, which is distant x from Earth of mass capital M. Now what will be the work done in displacing this body by a small distance dx? You know it is f dx. So we have gmm by x square dx. This is the work done in displacing this body by small distance dx. So work done in displacing this body from the surface of Earth, that is from r to infinity, from this to infinity, this is the potential energy. This will be the potential energy. So from r to infinity, this gmm dx by x square. You know it is x minus 1 by minus 1. You will put the value. What you will get? You will get v is equal to gmm by r. We could have directly also done this. We know what is potential. Sorry, this is not v, this is w. We know what is potential. It is minus gm by r for unit mass, and for mass of m it will be gmm by r. I started from scratch just to give you a revision. Okay. Now this is your m into potential. This is what? M into this potential, that is for unit mass, gm by r. Okay. Now if you want a body to escape this gravitational potential, what you will need? You will need energy, kinetic energy, which has to be equal to this. Then only you can escape. Let's say that escape velocity is ve, small this. Then you know what is kinetic energy? Half m v square. So this has to be equal to this gmm by r. So let's do this. What do you get? You get ve is equal to, see, 2 gm by r root over. This is the expression for escape velocity. Okay, it is 2 gm by r. But if you remember, acceleration due to gravity is given as gm by r square. So this is gm by r is g, small g r. So this is also equal to root over 2 g r. So you should remember these two expressions. You know the value of acceleration due to gravity. You know the radius of the Earth. If you put the values, you'll get ve is equal to 11.19 kilometer per second. So if you send a body with an initial velocity of ve from the surface of Earth, it will escape the gravitational potential of Earth. This is called escape velocity. Okay. From here, we'll develop another concept. What will be the velocity? What should be the velocity of satellite of Earth? See, velocity to be a satellite of Earth. Velocity of satellite. I'm writing it is, the meaning is velocity to be a satellite of Earth. Let's say this is moving in this circular orbit. This is r e. Let's say it is at a distance of r from the Earth. Okay, r from the center of Earth. Let this distance be small r. So from here we have r equal to re plus r. Okay. Now you know, I'm rubbing these. You know that the centrifugal force acting on the satellite will be equal to the gravitational pull. That has to be at equilibrium. Gravitational pull will be gmm by r square to this side, gravitational pull, and centrifugal force to this part, that is mv square by r. So this is m, if m is the mass of the satellite, mv square. Let's say we denote it as mv0. Escape velocity ve, this is vo. So this will be this this cancels this cancels this. So from here what do we get? We get V0 equal to Gm by R root over. Okay, so the velocity to be a satellite of Earth, that is root over Gm by R. But you know this is Gr, so V0 is equal to root over Gr. And if you remember, V is equal to root over 2Gr. So if you take ratio of these two, if you take V0 by VE, V0 by VE, it will be 1 by root 2, that is 0.707. So V0 will be 0.707 of VE. Okay, it is not able to escape the gravitational field of Earth. It revolves around the Earth. Okay, one thing I forgot to mention, why I have used this R. Well, this R was your RE plus R. This was radius of Earth, and this is the distance from this, if this is Earth, and this is R, that is distance from the surface of Earth. But this is about Earth's, this RE, VO or VE. Why I used it directly? Because this R is very less than R. This is 6 into 10 to the power 6 meters, and this is around 100 kilometers, 200 kilometers. So this R is very small compared to this. So we can almost say that R is actually RE. That is why we have used this expression. So you should keep this in mind. Now, from here, we'll understand what will be the path of a satellite when thrown from Earth. I'm using the term thrown with different velocities. Let's say this is your Earth. Now, if the velocity is this velocity, if we project a particle of mass m with a velocity which is less than V0, that is satellite of the Earth, to be a satellite of the Earth. V0 is the velocity to be a satellite of the Earth, and V is, this is escape velocity. So if it is less than this, what will happen? You'll project it, it will go, it will do like this, and then finally return back to Earth. Maybe return back somewhere else, but this will be the path. Okay. Now next, what if V is equal to V0? Obviously, it will go to certain height and then it will follow a circular path. Okay. Next, what if it is greater than V0 but smaller than V, escape velocity? Here what you'll have, so this is Earth, here it will go and it will follow an elliptical path like this in this case. And finally, if V is equal to VE, what will happen? See, if V is equal to the escape velocity, this is Earth, it will escape the gravitational potential of Earth. Now, what if it is greater than VE? This path is parabolic. When V is equal to V, it follows a parabolic path and gets escapes out of Earth's potential. What if it is greater than this? It will obviously escape and the path will be hyper parabolic. Okay, so these things you should keep in mind. You might get these type of questions in objective type questions. Now, when we are talking of elliptical paths, we should have a proper expression for velocity when it is moving in an elliptical path. You know about, I'm not going to teach you this. In elliptical, when you have an ellipse, you have focus F1 and F2, where this is situated. In case of Earth, this is situated here. Okay, or if this is Sun, Earth is moving like this. Okay, now if this is the point, then this point is called perigee, which is nearest, and this point is called apogee. Let's say this is VP at this point and this is VA. VP, that is perigee, will be greater than VA. Why? Because aerial velocity is constant. That you'll study in Kepler's law. Aerial velocity is constant. Therefore, this is at this point the velocity will be maximum because it has to cover equal area. Okay. Then you have term major axis. This is major axis. This, let's say this is A, and you have another term eccentricity, which is major axis by the focal distance. Okay. So these things you should go and revise in your ellipse syllabus. So let's say A is the semi-major axis, and this is E is eccentricity. Then I'm giving you the expression Vp, that is velocity at this, is root over Gm by A 1 plus E by 1 minus E. Okay, and VA, this is root gm by A 1 minus E by 1 plus E. So how to solve this question? We have two satellites orbiting around the Earth. This is Earth, its radius is r, and the first satellite is at a distance of r from the Earth. So this is first satellite, this is satellite A, and the second satellite is at a distance 3r. So this would be roughly around this. Let's say this is 3r. So this is your second satellite. Assuming circular motion. The question says assume circular motion. What we have to do? We have to find kinetic energy and potential energy, ratios of. Let's find out what energy we have. Now, and the question is clear. Let's rewind or revise our some expressions. Potential energy E U. This is the magnitude is basically mg by r. You have seen this. Unit potential is when you have unit mass, the potential is this, and when you multiply it with the mass, you get the potential of that particular mass. So this is this one. So for A, potential energy will be mg into m. Let's say the mass is m by r. What is the radius? You saw from center to surface is r, and then again this 2r. So this will be 2r. Clear? That is from center of the Earth, the radius is r plus r, 2r. And potential energy for B, this will be mg, mass is small m only, and this will be r plus 3r, that is 4r. So this is the potential energy of possessed by this first satellite, A satellite, and by B it is this. We have to find a ratio. So what is the ratio? This by this, that is, you see this goes up, this is 2:1. So the ratio of potential energy of A to potential energy of B is 2:1. Now about kinetic energy, we have seen velocity when a satellite is moving around a planet, it is equal to root over mg by r, where r is the radius. So velocity first, or velocity of A will be root over mg by 2r, the radius is r plus r 2r, and velocity of B will be root over mg by 4r. Okay, and the ratio of kinetic energy of A by kinetic energy of B, we have to find this only. This will be half mass of the satellite into VA square. So this mg by 2r by half mv square of this, that is mg by 4r. Again this cancels. This is 4r by 2r, that is 2:1. Okay, this is how we find out potential energy. This is how we find out kinetic energy, and when you are able to find it, you can find the ratio. So first of all, let's understand this question. It says this is Earth, and a satellite is revolving around the sun at a radius of r. When it's not written from the surface, it means when the radius is r, this means from here. Okay, and it's given that re is the radius of the Earth, mass of Earth is me, and let the mass of the satellite be ms. The question says that it starts to spiral down and fall, finally it falls on the surface of the Earth. So starting, we have at radius r, we'll have some potential energy and we'll have kinetic energy here. The total energy will be potential energy plus kinetic energy. It starts to spiral down and finally fall at the surface of the Earth, let's say in some time t. It says the rate of this dE by dt, the rate of fall is this minus c, that is energy is dissipating at a rate of c. So what is this? This is ct. This will be the total loss of energy. If it takes t time to reach from here to here, spiraling down, it reaches in t time. Then, and this is the rate. So c into t is the total energy that has changed from here to here. So what we'll do? We'll find total energy here. We'll find what will be the total energy when it reaches the surface of Earth. This energy minus this energy, that will be this c into t. Okay, this is the concept. Let's start. what is the total energy when it is at r distance? It will be potential energy plus kinetic energy. What is the potential energy? It is given as gm by r into m, that is, this is ms. And what is the kinetic energy? It is half ms and then gm by r, square of that. So this is gm e by r. Okay, and if you see, these two are basically same. So what it is? gme ms by r, gme ms by 2r. So this is basically half gme ms by r. This is the total energy possessed by the satellite when it is at r distant from the earth, it is revolving. What when it is at this surface, at the surface of earth? Your radius will be this. So on similar terms, the potential energy will be gm by r e, and the moment it reaches the earth, let that velocity be just that instantaneous velocity before it becomes zero. That will be this half ms gme re. So this is half gmsme re. Now what is the difference of energy? Change in energy. Change in energy will be Tr minus Tre, that is this energy minus this energy, and this will be equal to C into T. C is the rate of change of energy and T is the total time taken. So this minus this, you see these terms are common, half Gmems. What is not common? This R minus, sorry, 1 by R minus 1 by R minus 1 by Re. So if you, from here, if you just put C here, you get T is equal to this. This is the time taken by the satellite to finally fall to the surface, or the surface of the earth. But we have done a small mistake. How I realized I have done a mistake? Because see, this R is greater than Re. So when this is greater than Re, this means this will be negative, and time cannot be negative. It cannot be in minus T. So I realized there's some mistake. The mistake is here. See, this is minus and this is plus. So this will be minus of this. Minus 1 plus half. Again here, minus, and this will be minus of this. And so this will be just reversed. This minus this. So when you will take this, this will be Re and this will be R. Okay. This minus this. So this will be in minus and this will be in plus. So this is the value. Okay. So it's always good to just recheck your answer, whatever you have done, because looking at the answer only you will be able to figure out. If the figures were given, the values were given, you could have seen this was minus something. So that was wrong. So, okay. Now you see the question. We have our planetary body as this, and above this surface at 1000 kilometers, that is 10 to the power 6 meters, 1 into 10 to the power 6 meters, we have a mass of body, and we have to find escape velocity from this point. You know, escape velocity is basically equal to 2 mg by r, where r is the radius of the planet or sun, whatever it is. So if r is the radius of the spherical body, the escape velocity from surface will be 2 mg by r. So if it is at a distance, then, and at an appreciable distance, then we'll have to add this r plus this to find the escape velocity. So we have this very good question where it says that a body is at a distance 1000 km from the surface of earth, moon and sun. We have to find the escape velocity of all these. In all these cases, all the values are given. Mass of earth 5.98 into 10 to the power 24 kg, mass of moon 7.34 into 10 to the power 22 kg, mass of sun 1.99 into 10 to the power 30 kg. Similarly, we have radius of earth, moon and sun and the value for gravitational constant. Let's find out escape velocity from earth. I am writing 1 because this is not escape velocity of earth. This is plus this. So you understand what I am saying? This is 2 mg by r. R is radius of earth plus this 1 into 10 to the power 6 meters, because it is at a distance of 1000 kilometers from earth's surface. So let's calculate it. Root over 2 into m, mass of earth. What is mass of earth? 10 to the power 24. Then g is 6.67. This you should remember. 10 to the power minus 11 Newton meter square per kg square. by radius of Earth, it's given 6.37, and then add 1, so it is 7.37 into 10 to the power 6. So let's find the value. So the value is 10.4 into 10 to the power 3 meters per second. See, if you remember, it was 11.19 kilometer per second from the surface of Earth. It reduces to 10.4 kilometer per second at a distance of 1000 kilometer from the surface of Earth. Now let's calculate this for Moon. First of all, let's see what is the escape velocity from the surface of Moon, and then we'll do this just for understanding what I'm writing. It is velocity at Moon, escape velocity. I'm finding the escape velocity at the surface of Moon. So square will be 2 into m. Mass of Moon is 7.34 into the 10 to the power 22 into g 6.67 into 10 to the power minus 11 by radius of Moon. Radius of Moon is 1.74 into 10 to the power 6. So what do we get? We get it is 56.27 into 10 to the power 22 minus 17. So this is 10 to the power 5. So when you take a root of this, what you can do, you can, 5.6 or 10.6, 10 to the power 6 will be 10.3. So I'm doing 5. So you see, this escape velocity at the surface of Moon is only 2.37, which is 11.19 at the surface of Earth. Okay, now let's do the second part. When the particle is, or the body is at a length of at a height of 1000 kilometers. So what we'll do, we'll add here 1000 kilometers means 1 into 10 to the power 6. So this will become 2.74. So let's see what is that value. So it comes to 1.89 into 10 to the power 3 meters per second. So your Vm is 1.89 kilometers per second. Now let's see. First of all, let's see what is the escape velocity at the surface of Sun. So let it be Vs square will be twice m. M of Sun is 1.99 into 10 to the power 30 into g 6.67 into 10 to the power minus 11 by r. At the surface of Sun, it will be 6.96 into 10 to the power 8. So what do we get? 2 cross 1.99 cross 6.67 divided by 6.96. It is 3.814 into 10 to the power 30 minus 19. So 10 to the power 11. So let it be 10 to the power 10. So this is, so it comes to 6.18 into 10 to the power 5 meters per second. That is, the escape velocity at the surface of Earth is this much. That is, if you multiply 618 kilometers per second, it is 11.19 kilometers per second at Earth, and it is 618 kilometers. So much bigger value. Now let's do the same thing at height of 1 into 10 to the power 6. This will become, instead of 6, it will become 7. So let's find the value. So we take a root. It will be 5.77 into 10 to the power 5 meters per second. Okay, this is the value.